also why I'm interested in analog gravity studies, because they're based around two principles, which when I was studying were the things that fascinated me the most in physics. And the first thing is, when you do physics, you have always a rather complex system, and what we do is we make, as it seems sometimes, a million approximations, we throw things away, we make the system so simple that we can actually solve it. And when you do this, still, it seems that it describes in some parameter space, perhaps it describes very well what's going on. So the second one is, and I think this is related to the first one, is I can have two seemingly very different systems, and yet in some circumstances, these two systems can look alike in the sense that they exhibit the same properties or the same behavior. So that's really the base of the core of analog gravity studies. So, and now coming back to these three seemingly very different images here on my first slide, I will explain or hope to convey the idea why a bastard vortex flow can look very similar to fluctuations in a bastard vortex flow can have the same properties than fluctuations around a black hole. So what you see here is a picture by Roger Penrose of a depiction of a black hole. You have the singularity in the center. Here you see the sound cones, future sound cone here in the past, light cone. Here's light cone in the fluid with the sound cone. And what you can see is that when looking at these two systems and you look at the fluctuations, and you can then show that in both systems, fluctuations underlying the same amplification process, which is known as Hawking radiation. So that was just a very vague description, but of course I have to give you some more details. And let me give you an overview also of how analog gravity systems have been discovered, and what these analog gravity systems are really. They are a possibility of analog simulations of classical and quantum field theory in curved spacetimes. So, choosing thought because George has encouraged me not to use many equations, and I thought maybe rather than me explaining what an analog gravity system is, let me show you a popular science explanation, perhaps, which is taken from a video clip from a TV series, which is called The Big Bang Theory. Probably all of you know it. The ones who don't know this theory, it's a very unusual theory in a sense. Usually all of these TV series are based around the life of lawyers and doctors. Here it's different. It focuses around the life of 4 physicists, or 3 physicists and 1 engineer. And one of them is Leonard here, on the right. And Leonard has some very exciting news for his girlfriend, Penny.
So listen, do you remember when I said the similarities of the equations of general relativity and hydrodynamics suggest you could find the equivalent of Unruh radiation in a large body of water?
I thought I said that to you.
Anyway, Stephen Hawking's team is looking into that, and I've been invited to join them.
Wow, Hawking, good for you!
Oh, it is, just, I'd be gone for a while.
Well, how long?
3-4 months.
Whoa. When would you leave?
A couple weeks.
Oh, okay, well, I'll just come visit you.
That's the thing, you can't. I'll be on a ship in the North Sea.
On a ship? Aren't they afraid Hawking will just roll overboard?
He's not going to be there, he's just sending a team to research his theory.
Oh, sure. Like when you send me to kill spiders in your bathtub.
So, also, of course, that was a very nice explanation. So we'll go through this this idea step by step, and then also let's at the end resume back to this clip and find all the errors and mistakes. So let's first start very basic. I apologize if all of you know this, but sometimes it's good to build up gradually. So what is a black hole? A black hole is a region of space-time from which gravity or the gravitational pullback is so strong that nothing, not even light, can escape. So as I pointed out before, here this is this picture by Roger Penrose of a black hole. You have this wiggly line here in the center is a singularity. You have two different objects here. These are these light cones, the future here, future light cone, and the past light cone. So if you're in instant time in this point here, all your future has to be within this future light cone. And so there is, around the singularity here, in the center of this black hole here, there is what's called this event horizon. And if you are outside this event horizon, you can still escape. If you're beyond this horizon, all your future light cone is tilted towards the singularity, and you will fall into the black hole and you can never return. These other things here are vacuum fluctuations, and it's kind of a picture of the Hawking process, but I will come back to that in an instant. Now, how can you find an object like that in a hydrodynamic system, as Leonard explained initially? So, about 30 years ago, Bill Unruh gave a lecture on fluid dynamics, and he thought about this analogy. He thought about, what if I have a flow that goes supersonic? What happens to the sound waves in the system? And then he went back to his office and he worked it out, and this was the beginning of analog gravity. So now let's go through this in detail. So here again, we have these two seemingly very different systems, our black hole on the left, and on the right we have our fluid dynamic system. Now let's look at sound waves, and let's assume, let's look at sound waves where we have in a river flow, but the river flow initially here on the left is almost zero. So if I look at sound waves, how they propagate in the system, if I initiate a sound wave at that point here, I see it propagates equally fast in all directions. So let's now assume that the river is speeding up and it's going in this direction. And if you see now, my sound waves are propagating faster with the flow than against it. Now imagine you have a flow that becomes, so the velocity of the flow becomes equally large than the propagation speed of the sound waves in the system. So at that point here, the velocity exceeds the speed of sound. So suddenly a perturbation, a sound wave initiated at that point, it cannot propagate to the left, it can only be dragged along with fluid flow, so basically everything is propagating to the right. And so here we have a supersonic flow, and here we have a subsonic flow. Now let's assume Sabine is sitting here and Church is sitting here, and I want to discuss some issues about the workshop. And Sabine would, the only way of communication would be through the sound waves in his water, so Church could tell Sabine a lot. He's sitting here, all these sound waves which make it into this critical supersonic region, while Sabine here would have no way of communicating back to Church. So this is how these analogies work if you think of, in a way, of a Gedanken experiment, but the analogy is much, much deeper. So at the first level, so they realize that perhaps fluids can exhibit these effective horizons as seen by these small fluctuations, in this case are the sound waves. However, then when he worked out the equations of motion for these little sound waves in the systems, he could find a more precise description, and indeed he says that this small perturbation experience an analog effective emergent gravity system and a magic tensor or an effective gravitational field. So this sounds very difficult to understand, but in fact it's really trivial, and it works this way. So we have to do a little bit of quantum field theory in curved spacetime, but promise it's very trivial. So every one of you probably knows the wave equation. Now, the wave equation here, as we all know it, can be rewritten in, let's say, a more fancy way. And that means I can rewrite it in a relativistic way by simply saying, oh, I have a flat space-time geometry, and I can here combine space and time in this metric tensor here, and there are only constant. Here's the speed of light, so not here on the diagonal here. This is spatial part here, and they're only the ones on the diagonal. So in some sense, these two things are simply the same equation. It's just a different way of writing it. Now, this seems perhaps not so useful, but if you wonder what happens to my wave if it doesn't propagate in flat spacetime, in this room here, for example, what if it propagates nearby a black hole or a general curved spacetime geometry? What if the gravitational field is not simply flat? So then what you can do, it's called a minimal substitution. All you have to do at this point is say, oh, let me replace my Minkowski spacetime, my eta AB, with a more complicated spacetime geometry with a gravitational field GAB here, and now all of these entries can be functions of space and time. So, in some sense, whenever you see this guy here, over here, then you know already that, oh, that's just a wave propagating on a curved spacetime geometry. So this was precisely what Bill found. He said he started with the fluid equations, which are, probably all of you remember that from studying or continuity equation, Euler equation. So these are simply the equations that describe a hydrodynamic system. You also have the equation of state. But nevertheless, so he starts from these equations, and if you then perturb these equations, you get how, and you're assuming that the fluctuations are small, you get the equations of motion for these fluctuations in these systems. And you can actually rewrite those in this way. And if you remember the previous slide, that just tells you, oh, that's just a wave equation on a curved spacetime geometry. And the trick Bill did then, it's just a rewriting again of these fluctuations. He introduced what's called this effective acoustic or emergent metric tensor. And what's inside here now, these are all properties from the background flow. So in particular, it's V is the velocity of the flow, and C is the propagation speed of the sound wave. Now, if you also remember the Gedanken experiment from the beginning, remember I said, well, if the speed of sound is equal to the background velocity, this is where I get my effective horizon, and that's precisely for the ones who have maybe more gravitational background. This is when this G00, this first entry here in the metric tensor, is becoming 0, so it goes from minus here through 0 to plus, and this is where we have our effective horizon. So again, the assumption that has been made were that the fluid flow is inviscid, irrotational, and incompressible, and in this particular parameter regime, you can map the hydrodynamic systems, the behavior of the fluctuations. You can map that one-to-one to quantum, to, at that point, classical field theory and curved spacetime.
So with this, I understand that you get to supersonic flow and you can't move sound the other direction. In my head, I think about planes that are going supersonic.
Right, coming to
And then, but this last one, the fluid velocity, how do you get, the sound seems to be going in advance of the object, or?
no, not in advance. So the flow here, so what's happening here, it's equal. Here the flow is even faster. So here it is really, it's exceeding the background flow, it is exceeding the sound speed. So it has actually get the same thing in these airplanes. I'm coming back to that.
Okay.
So maybe we can wait a few things. So basically it's just, at that point they're equal. Here, the flow is even faster.
Okay.
Okay, now, that sounds crazy, and of course, as just pointed out, there is an issue here. Supersonic flows, that seems a little bit, you should get the attention level is very high, because whenever you go supersonic, you encounter easily shock waves, and shock waves, what that means is that all the parameters in the fluid flow instantaneously change, and this linearization process, of course, is no longer valid. So this idea that the fluctuations are small, basically, that I can assume that it's irrotational, inviscid, and incompressible. It's not incompressible anymore if you get the shock wave. However, when I said small fluctuations, the analogy does not only restrict itself to sound waves, you can also look at fluctuations on the free surface. So for example, surface waves. And the analogy just carries through. If you have to modify, you have to apply certain boundary conditions on your fluid dynamic system, but still you can linearize and look how small perturbations behave, and you get the same behavior again. You can describe the propagations through this simple wave equation on curved, in a general curved space-time geometry. Now, given that it works for this as well, in fact, all of you have really looked at analog space-time. And the system I'm talking about is actually the kitchen sink when you do your dishes. And if you're lucky, the water tap is not precisely above the sinkhole, so it hits the flat surface. And then what you get, perhaps not in such a nice way, but because here they use silicone oil, but the same goes for water, as I will show in a while. You see this kind of behavior, this kind of pattern. So the water would hit the metal plate of the sink, the bottom of the sink, and then you would get this ring around. Inside this ring, everything is very smooth, and outside here, you would have what's called usually hydraulic jumps, so here you have a lot of wriggles. So what that actually is an analogy of an effective white-hole horizon. So what is a white-hole horizon? So a white-hole horizon is a time reversal of a black hole horizon. So if I have a black hole, nothing can everything can enter, but nothing can escape once you're beyond the black hole horizon. In a white hole horizon, it's the other way around. Nothing can enter, but everything can leave. So in the river flow, imagine now you're in the opposite situation here, in a situation that here the system is subsonic, here it's supersonic. If I want to send in a perturbation from this direction, it can also only propagate up to this effective white hole horizon, and then the wave is arrested. Now, and this is what's happening in here, because the flow is very, very fast here, and this thing, the flow exceeds the propagation speed of the little ripples on the water surface here. So that's very smooth, nothing can propagate here. And at that point here, because the radius gets larger and larger, so here the flow has to slow down, sorry. So here the flow is slow enough again, so on this side it's subsonic and here it's supersonic. So, and if you like, you can simply repeat this experiment in your kitchen sink. I have done that. One thing what you can visualize this behavior. You can actually look at this so-called the equivalent of these Mach cones, which are called here the Froude cones, and which simply see if you would take a little stick here and you place it in different distances from the center, you can see there's this opening behind, and the angle here is related to the ratio between the background velocity and the velocity of the surface wave. And if you take a disc and you put like pins here on different distances, you can see that this cone here gets steeper here, and it opens when you go to the edge. So in this way you can map out some of the behavior, and in fact really every one of you has looked at an effective white hole horizon. So now you could say, well, this is very neat, maybe to explain your child how black hole or white hole horizon works, but can we use that for something? Can we make some use out of it? Can we use that to advance our understanding of classical and quantum field space? So, and coming back to the original paper in '81, so the title Bill chose at that time was Experimental Black Hole Evaporation ? And what he realized back then, well, if the two systems, my fluid flow on the one hand, and my fluctuations around black hole geometry, if the equation of motions are the same if all the approximations in both systems are valid, these two fluctuations have the same behavior, we should also see the same effects to arise in these systems. And in particular, he was thinking of Hawking radiation. He was posing a question, can we use that system to experimentally mimic black hole evaporation? So, in more general, like this is also, these are the three different effects I will discuss, which we can see or which we hope to see in this analog gravity system. So the first one is this experimental black hole evaporation. The other thing, we can also mimic rotating black holes. We can look at super radiant scattering from rotating black holes. And we can also look at cosmological particle production. And the real value of these systems is really that you can say, well, it is a good approximation. It's a good analogy in some parameter space, but of course if I look at my fluid flow, there are a lot of deviations. And the key question is these other effects which we're looking at, are they robust against these deviations? So you can actually experimentally test the universality and the robustness of Hawking radiation, super radiant scattering, and cosmological particle production. And that is very important because we're still lacking a definite quantum gravity theory. And quantum field theory and curved spacetime, there are sometimes reasons to believe, for example, if you look at black hole evaporation process, if you look at the radiation coming from the black hole and you would, for example, trace it back to the black hole horizon, you would get a tremendous blue shift. Blue shift to energies where you say when you come closer and closer to this horizon, you get blue shifted to energy scales where we simply don't trust quantum fields in curved spacetime anymore. And one would feel perhaps a little bit uncomfortable with the lack of a quantum gravity theory to describe what's going on. So the question is really, does, for example, Hawking radiation really probe the UV physics? Or can I still describe it with quantum fields in curved spacetime? And the same question arises in these analog gravity systems. If you think about it, if I have a fluid flow, and if I go to shorter and shorter distances, eventually you have to think of the molecular structure of water. Or one level before that, it is a dispersive medium. So will these kind of deviations, will they alter the Hawking process, or is it such a universal and robust effect that it doesn't matter what the UV physics is? So this was one of the motivations I think Bill had in mind, to see how independent of the system these effects really are. So coming back to the Big Bang theory, and now let's do some corrections. So first, quite funny, because Bill told me that actually they called him to get the pronunciation of his name right. That's very good, but apparently they didn't care so much about some other details. So one was, they said, like, Hawking wants to detect the Analogue radiation. In fact, it's Analogue who wants to detect the Hawking radiation. It is in the hydrodynamic system. You don't quite have to go to the North Pole. You can actually do that in an undergraduate laboratory in Canada, in Vancouver. It's a very beautiful place and much, much warmer. So let's start with this experiment, which was described in the Big Bang theory. And this is, I found it on the web. There are actually fantastic images out there. This is how journalists imagine us working on black holes. It's actually not so far off. We have a lot of cameras, not so many microphones. So anyway, so let's start with perhaps the most prominent case studies on black hole evaporation in the laboratory. So in order to do that, let's start first. One has to get a general understanding of what really is Hawking radiation. We have to get a certain understanding of this effect. The second is, how can we set up a tabletop experiment to conclusively test Hawking's Penrose prediction? And so what does it really mean I have detected one of these effects, in particular here Hawking radiation? And why is it of interest? I've already said that. Why is it interesting to to run these analog simulations. So let's go back again. So classically, nothing can escape a black hole, but if you include quantum effects, it can evaporate away. So Hawking radiation is a very, very important process because it tells us what the final fate of a star is. So a star can collapse, can form a black hole, and the question then is, what is happening to it? And the Hawking process is important because it is a process that allows a black hole to radiate away their mass. So now, Hawking radiation seems like a very exotic effect. It isn't really. So let me first start with this very popular explanation of Hawking radiation, which is also taken from, I think I also took this from Roger Penrose's book, but anyway. So the first paper on it was in 1974 by Stephen Hawking, and perhaps a naive way of understanding what Hawking radiation is about is the idea is that if you have vacuum fluctuations, so the vacuum is not really empty, you have these fluctuations here, these are these wiggles here, and all the time you, perhaps if you like, you can think of creating particle and antiparticle pairs. And when this is happening nearby this event horizon, this black hole horizon here, the gravitational force is so strong to separate these particle pairs, and the particle is getting emitted away and the antiparticle is falling into the black hole, while an antiparticle has a negative energy and therefore it reduces the energy. It is the mass of the black hole. However, I personally don't like this explanation at all. There's a very simple way of understanding. It's a very simple scattering process. And it's actually so simple, which also takes a little bit of the myth away of Hawking radiation, but this is how one can understand Hawking radiation in a more feasible or more down-to-earth way. So what is really a black hole? So a black hole has a gravitational potential, right, if I'm zooming in this area, this gray area here, and it has a boundary, and the boundary is this event horizon. So the boundary condition I'm putting on here is that nothing can escape. Now I can now say, let me look at my fluctuations here. Let me not specify if I'm talking about classical or quantum fluctuation. Let me just look at small field fluctuations outside my black hole. Now, if I'm focusing on the radial direction, I can say, well, in general, always I have a second order wave equation, so I have two solutions. I have in particular here, if I want to right or left moving mode, so inward or outward of the black hole horizon. In general, I should have that on both sides. I have not yet imposed my boundary condition. Now, let's think about it a little bit in a different way. So, presume I have a conserved quantity, right? So then I could write that as an elastic scattering process. Now, there is such a thing, which I can get from the wave equation. Remember the wave equation of curved space-time geometry. I can actually derive such a conserved quantity. Sometimes it is referred to as the energy. Personally, it's not always correct, also the norm. The most correct, in general, way to describe it is called the particle current, never mind what it is. You can calculate that from, in the analog systems very easily. It is related to the amplitude, to the frequency, to the velocity of the wave. Now, if you look at this scattering process now, well, if it's an elastic scattering, everything that goes into the potential, now we basically look inside and outside, but everything that goes into it also has to come out again. So now imposing the boundary condition, that tells me that nothing is coming out. Okay, so this solution here is gone. But at the same time, I can calculate this conserved quantity. Let me say I'm sending in one. I can readjust my units any time, so I say whatever I'm sending it has amplitude 1 or 1 particle current. It's just a redefinition. And then what I can see is here I can calculate these quantities, and if I replace that here, what I realize that this guy here on the right, which is going into the black hole, has a minus sign in front. So it seems almost as as if it would source the whole process. So this is what is referred to as this negative energy partner that falls into the black hole. Remember, here we're inside the black hole. And what we're seeing here is that, so this is the guy that's coming out, this alpha squared, this is the guy that falls in, this is minus beta squared. And what we see, because it's 1 here, so for this equation to hold, what's coming out has to be bigger than 1. What that means is you have extracted energy or particle current out of this process. So and that's basically how what's happening to the field fluctuations around the black hole horizon. It's just a simple scattering process. Once you got the right conserved quantity, you can work it out. It's really trivial. And how can you associate a temperature to this effect? It's also very trivial because you can compare. You can actually say, okay, let me say, what if I look at the ratio of how much is falling into the black hole with respect of how much is coming out, if I write that down, you can see that that actually has the form of a Boltzmann distribution. So you can calculate this quantity from the field theory side. And what's the only thing it depends on really is the surface gravity at the horizon. So the whole process is determined by the gravitational field, the strength of the gravitational field. And if I now compare that with a standard Boltzmann distribution where there's a temperature, I can actually associate a Hawking temperature to this process. And this is why black holes have a black hole temperature. Now, I've been very careful here because it's very important. I have not specified what kind of fluctuations I have in mind. I just said that this is an amplification process that works in a certain way. You also have to stimulate it in the right way. But this is this amplification process. And black holes are linear classical quantum field amplifier. So now this amplifier works in a particular way, right? It isn't sourced to hasn't a power plucker, so it takes its energy from inside. It basically evaporates away its mass by absorbing negative particle current fluctuations. Now, it has, in order to detect this effect, you have to look at perturbation process, right? It's always these two guys, one is falling in, the other one going out. Remember, this scattering process has, one is going in, and then these are the two, one, you send it in, or it takes a fluctuation and it converts it into these two fluctuations. The one that goes into the black hole and the one that comes out. It should follow this kind of behavior, which is that it can associate a Boltzmann distribution to it, and it is the distribution only depends on the surface gravity of this effective horizon. So that's basically what this process is about. And when you want to set up an analog gravity experiment, in my opinion, you should try to see how much can you recover from these properties of that effect. So now let's come back to, because we're doing a perfectly classical experiment, and usually people would say, oh, you want to see Hawking radiation, it's quantum. Now, the thing is the following. If you look at any analog system, any system in a lab, even if you work with, of course, ultra-cold atoms, whatever, superfluids, it's not always, you're not at zero temperature. Which means, of course, if I have zero temperature, all that's left with is my quantum noise. Well, if I have a non-zero temperature, then I have thermal fluctuation, I have thermal noise in my system. And if, of course, you go a little bit, there's a huge magnitude separation of amplitudes here, of course. But then beyond that, I have classical noise, vibrations, and all these kind of things. And even beyond that, you can, for example, stimulate the system and excite a certain fluctuation in your analog gravity system. Now, what we are doing, we are running this amplifier at this level. Huge order of difference, but we say, well, the classical amplification should follow, if it is linear up to this scale, it should follow the same physics. In order to go, we could, in this particular experiment, we can never go down here, but people now try to repeat these things where there actually is a chance to go down to this level. So, I don't even try, so the question is now, so is there no difference between this classical equivalent of Hawking radiation, or what we call a stimulated Hawking process, and this quantum quantum Hawking radiation. The difference is this pair of modes created, if you go down somewhere between here, you can calculate this threshold where you are, then you will see that the correlations between the guy that falls into the black hole and the guy that's being emitted away, that these are stronger than classical correlations, that they can be entangled. And that depends very much how close you come down here. Now, I've already talked about that. The issue is about testing how dependent this process is on the UV behavior of the system, of how the system really looks like at small scales. Now, this is the experiment we did together with Greg Lawrence. He's a civil engineer, he's a professor in civil engineering. He's a postdoc, Ted Tedford. And on the other hand, I was Phil Andrew, Matt Penrose, who's an honors student at the time. He's now my PhD student, and myself. And we did a very simple experiment. This is our setup. It's one dimension, it's an open channel flow, which is in the civil engineering building where undergraduate students test some aspects of Bernoulli equations and do some of their experiments, they're part of their coursework. So, how it works is we have this water flow, we have the obstacle in the flow which changes the depth of the water. This is a water reservoir, water gets pumped back in, it's a stationary flow. And the back end here we have a wave generator sitting that stimulates the system. Now, the basic idea is that, as I mentioned already, this analogy also does not only hold for surface waves, for sound waves, it also holds for surface waves. And the reason why it's much easier to work with the surface waves is because actually their propagation speed is proportional to the height of the flow. So the shallower they is, the slower they propagate. At the same time, if you have a constant flow rate in the system, the shallower the flow, because of conservation of mass, the faster the flow, the fluid has to speed up, the faster the fluid flow is. So if you decrease the height of the flow, you speed up the background flow and you slow down the fluctuations on the top. If you remember the acoustic line element, here it's not acoustic, you should really say effective because it's now for surface waves, not sound waves. And what you see here is that this is exactly what you want. You want to find a region where those two are the same, the propagation speed of the fluctuations and the background flow. Now, what you get is actually a set of effective black and white on horizon. And it's again here, the flow is speeding up, the perturbations are slowing down. So here you get the black on horizon. Then at this point here, the flow is slowing down again and the perturbations are picking up. Now, this is how the experiments look like. This is, of course, very much at the beginning. In the end, we generated waves which were about a millimeter of height maximum. This is just for demonstration. So we send in waves downstream, the downstream end of the flume. The waves propagating up to a point here. As you can see, they cannot propagate beyond a certain point, and here is roughly where the effective light on the horizon lies. And the question really is, what is happening exactly to this wave when you penetrate the effective light on the horizon? What we're doing actually is, in order to get all the information, we look at the free surface of the system. And what you can actually see, you send in a particular wave here, and this is the ingoing wave, and you can see it actually gets converted to a pair of waves. You can filter everything else out. Here's a superposition of these positive and negative particle current waves. You can look at it also separately. You can do an inverse Fourier transform to simply just leave these positive and negative norm partners there. And then you can also test all the other aspects, as I said before. You can actually see how much is actually converted to this positive norm or negative norm waves. And you can actually find appropriate quantities to show that indeed they're following this Boltzmann distribution. And as a last step, you can simply show that the slope of this, which should only be determined by the effective surface gravity, is indeed, you can also get the surface gravity simply from the background flow. You can compare that with the excitations, and you can see that both are the same. So, hope that wasn't too detailed. But this was just an example to convince you can actually use these analog gravity experiments, and the same principles for the later experiments will be repeated in other systems. So it's it fulfills these three quantities here, and now we can go back and ask ourselves, so what if I could cool down this system to temperatures, to very, very small temperatures, close to zero temperature? What will be the temperature I have to get to? What is the temperature of the effect? And the temperature of the effect is 10 to the minus 12 Kelvin. So there is simply no way of ever seeing any quantum effect in such a system. So now people used other systems, such as optical analogues of the event horizon. And let me quickly explain you, the idea is the same. This is why I also took my time in the first experiment, because the principles are the same, we just have to replace some things. For example, the sound waves or surface waves, and of course, are now replaced by light. It's an optical system. So the equivalent of the river flow needs, whatever that role plays, needs to exceed the speed of light in this medium. And that's, of course, it seems rather impossible. However, you know that in mediums with a refractive index, you can use mediums such as water or glass to reduce the refractive index of light. However, you would need something that drastically reduces the refractive index. And such system exists, for example, in fiber optics, which is also used for telecommunication. And how it works is that information carrier light pulse is confined to the core of the optical fibers. So you have these light pulses, which propagate through the optical fiber. And what's happening is that every pulse of this is actually modifying the refractive index in the system. And depending on the intensity of this light pulse, you can, the higher the intensity, the more you can modify the refractive index. So when this light pulse is propagating through this media, it changes the refractive index. And this is also called, from the viewpoint of the moving pulse, this looks like the media is really moving, also the optical fiber is not. It would be the same if I were to repeat the water experiment. Rather than having a water flow, the water flowing, I could have the flow. Imagine I have an infinitely long flume and have the obstacle, and I can move the obstacle through the flow. So, right, so the pulse is establishing a moving media. It's also called the Kerr effect in nonlinear, there should be a nonlinear fiber optics. And the medium naturally moves with the speed of light, because it's a pulse itself. So how does it work? If I have this light pulse here, and let me assume I'm probing this light pulse now with a probe pulse, I can see, this should be probe pulse, that when the probe pulse is slowed down by the pulse until they have the same group velocity. And then what then is happening is, of course, this is basically, it can propagate up to this point, then it's being slowed down because this pulse is modifying the refractive index. It slows down this probe pulse. And then you have, of course, again, it's also a dispersive media. The dispersive effect can actually release this blue shifted probing pulse. Now what you get here is also a set of white and black hole horizons. So at the back part of this pulse you have this white hole horizon, the front part you have this black hole horizon. This is how you can understand this analogy here. But without the probing pulse, the idea is that already here you get this white hole horizon coming here, and it's also emitting this pair of photons, this positive and negative photon pairs. And one of the things, of course, in this nonlinear medics, you have nonlinear effects, so it's a much more difficult system actually, and it's not so well understood exactly precisely what is happening. And one of the things, for example, you have this modification of this pulse here, and that's because of this deepening of the pulse is equivalent to this optical shock. So everywhere you encounter these shock waves. Now, there have been some very nice results already. Oh, I wanted to actually, so I have to do this now. Oh, it's gone. There was something beneath that. Sorry. There was a paper. There was meant to be some text beneath it showing the paper by Daniele Faccio and his group. Was published in PRL. And what they've done, they set up such an optical system, and they looked at this propagation, sodium propagation in a dielectric medium, and they've seen, they observed the evidence, as I said, let me just read that to you. We report the experimental evidence of photon emission that on the one hand bears all the characteristics of Hawking radiation, and on the other is distinguishable and thus separate from other known photon emission mechanics. So what they've done, they couldn't quite show the same three features as we showed, which is simply because they can, for example, not really calculate or know the shape of the pulse. It's very hard to reconstruct the shape of the pulse, which is also related to the gravitational surface gravity in this particular system. They also had some other things, that the radiation was sent perpendicular to this effective horizon, so there's still some open questions to be resolved. However, it's a very interesting system, and yeah, so it's very promising. So Daniele still also looks at other media to see some media which might be more appropriate to repeat this experiment to get some more information of what is going on. Now, at the same time, more recent than that, another paper came out, and they looked particular. They said, if I send in a soliton pulse, can I see this conversion, because it's also this dispersive medium, can I at least see this conversion to positive and negative norm modes? They call it negative frequency. It really should be called negative norm radiation. And what they've seen is that depending on the input power of the pulse, you can see there is a regime where you get clearly two of these. So they have they send in some soliton in fiber optics, for example. They use these two different systems. Sorry about that. So they use this. They repeated. These are two groups. The one group is Daniele Faccio again. The other one is Friedrich Koenig. And they look at, in Daniele's case, again in bulk medium, and in Koenig's case in photonic crystal fibers. Now, and what they've seen here already is that they get this nice result, that you really get this decay of this pulse into this positive and negative frequency modes. So the question is now, for example, to look at correlations of these two partners and to see this, but it's a nice example of how these analog gravity studies motivated to look for such an effect in optical systems. So what else? Other black holes. So where are we at that point? As I mentioned before, it would be great to repeat all this experiment at lower temperatures so that you can access the quantum Hawking radiation. And one of the people who has made some considerable progress is Jeff Steinhauer. He's working in with superfluids, Bose-Einstein condensates, and what he found is that he was able to set up a background flow that exhibits a black hole horizon. He has not quite seen the effect, but if he would take this background flow and uses some numerical simulations, he thinks that the parameters are already very promising, that you can actually see the effect should be there, but it's a matter of detecting it really. An alternative proposal is to use a different boundaries. So instead of having an open system, one that's closed. So if you're looking at toroidal Bose-Einstein condensates, or the condensate is spinning around, the velocity is going in this direction. And again, you here get a black hole horizon and a white hole horizon, similar to the setup I was showing in the open channel flow. The way to get that here, for example, was suggested by Fuchs Chain to, for example, use quantum de Laval nozzles here to simply tighten, have a stronger confinement here, so to speed up the flow, and here to have another Laval nozzle to slow it down again. However, because of the different boundary conditions, you also get instabilities here. So this kind of, be it Bose-Einstein condensate, superfluids are being used in for other purposes, for metrology measurements. But perhaps one can also use them to look at traces of Hawking radiation. But here also, because of the fact that it's a closed system, you can also encounter these instabilities. So it's not so clear, but this is also a very interesting field, interesting setup to explore. So I think here is a natural break because now I'm studying with a different system.
Great, thanks so much. Now,
So now coming back, initially I said I would like to talk about, in principle, so I talked about black hole evaporation, and then now I want to talk about cosmological particle reduction, and then super radiance. There would also be unradiation, but I won't cover that. So, and we were talking about a perfect analog gravity system. I was asked this question, isn't it? And I think for me, where the analogues work the best, because they are the best amplifiers, is actually we come to the possibility of mimicking cosmological particle reduction. So let me get right into this. Let me first explain you a little bit about, tell you the story about cosmological production, particle production, why it's also, and all of these effects are amplification effects. They can all be understood. They just have different, if you think about the stimulated versions, what are you feeding into the system? What is how do you stimulate the system? But anyway, all of those are amplifiers, and one thing which is very promising, also has some very nice results by Chris Westbrook already, is cosmological particle reduction. So first I will talk about how it works. Then again the question, how can we set up a tabletop experiment to mimic that mechanism that is responsible for the creation of particles in our universe. And then, again, why is it interesting to do such simulations? Now, again, sorry if I'm a bit too detailed, but let's start again from the basics. So, you can also write down a gravitational field that is matching our observations of the universe as a whole. And what we can see that it is expanding, which we know from the redshift of the spectra of distant galaxies. So one very popular way of explaining it, imagine you take a balloon, you don't quite fully fill it up with air, and you put little dots on the balloon, and then you keep on blowing air into the balloon, and then you see that all of the dots on the balloon moving away from each other, further and further away. So this is what we're seeing. If you look in all directions, it seems that our universe is expanding. It seems on a large scale, it seems isotropic, uniform in all directions, homogeneity, no large scale formation. So, and there is one unique space-time that describes all of, describes also these expanding universes, which is this Friedmann-Robertson-Walker type universe, that's how they're called. And you can actually, you don't even need the Einstein equations to show that that is a unique solution. Stephen Weinberg did that, I think, in his PhD thesis, where he looked at maximally symmetric three-dimensional subspaces with positive eigenvalues, and you can see that this is the unique solution. So there is some sort of gravitational field that really uniquely describes our universe as a whole. So now again, remember how can we get that? Now, what I'm focusing on, I will show you how you can recover such an effective space-time geometry from a superfluid. And when I say that, it's again, have in mind that in all of these analogues, I had this, when you look at the small fluctuations, you had this wave equation on this effective curved space-time geometry, and it's all a matter now of, because this geometry depends on the parameters of the system, so the speed of sound and the background flow and so forth. So if I want to set up a different geometry, different, for example, than Hawking black hole geometry, then I would have to tweak my system externally such that small fluctuation in the system see this, for example, expanding universe, or they propagate to they experience this Bose-Einstein condensate as an expanding, effectively expanding universe. So how can we understand that? How is that working? So first of all, what is a Bose-Einstein condensate? It's ultra-cold gas of atoms. It's a trapped gas of atoms, right? It is, we are in a cold collision regime, as we call. So you only look at the bosons, only two particle interactions. They only collide. They don't form molecules. And what you can do, if you cool this system down to temperatures low enough, you have this condensation, you have a phase transition, and you can replace your bosons, your field operators. I shouldn't say that, but you can basically describe it as a macroscopic fluid. And this macroscopic fluid is irrotational, inviscid, compressible, so it's precisely where the analogues work very well. You can describe it, it has a density and it has a phase. It's random, but it has a phase. It takes a phase. Now, what is very interesting is, if I look at small fluctuations in such a system, right, I can look at sound waves again in such a superfluid, and the speed of sound depends on the density of my condensate. And it also, so basically density is given a number of atoms which are in a condensate divided by the volume of density. And then I can also look at, there's another thing that enters here, which is this U of T, which is basically the interaction strength of the atoms. So how strongly these atoms, these bosons, collide with each other. And interestingly, what one can do, for example, one can change the speed of sound as a function of time. So if you do that, so one way, which is very simple, it's very easily can be done and has been done many, many times in many experiments, is to change the interaction strength. So imagine you have your Bose-Einstein condensate sitting in your trap, more like this, not like this, but let's blow it up. And then what I can do is I can use external magnetic fields, and you can change these interaction strengths via what's called a Feshbach resonance. If you use the right kind of atoms, you can do that. So now let's assume we are all sitting in this condensate, we're part of this condensate, and we exchange information. All of us send, every second, we send sound waves to everyone in this room. We send it to various people. Now, let's say I'm not part of this, I'm outside, and I'm changing the sound speed in the system. And the way I'm doing it is making it slower and slower and slower and slower. So you're sending every, if an internal clock, you're sending off your signals with a certain rate. And you realize all the signals from the other people take longer, the distances between the signals to arrive get longer and longer, because the speed of sound is slowing down, slowing down, and slowing down. So the distance where I'm receiving information from other people gets longer and longer. So now there are two explanations. One is, of course, if you know, well, somebody's playing with the speed of sound. The other thing could be, what if it's a situation like on this balloon, where let's assume that there we have, in the real universe, we have the speed of light, which is constant, but the universe is expanding. So you have this redshift. So now here, in this situation, it also looks for small fluctuations in the system. If the speed of sound goes slower and slower and slower, it seems the time, for example, it takes to propagate from one end to the condensate to the other takes longer and longer and longer. It seems that the condensate is effectively expanding. And that's precisely how you mimic this expanding universe versus. Now, again, one particular interesting case is, for example, if I want to, what's called, which is related to inflation, it's this de Sitter universe, and that has a very particular form. Let's come back here. So, in some sense, these are this kind of Friedman-Roberts and Walker universe, and then depending on how I basically change this particular parameter, which tells me if I'm on the distances on a spatial slice, how they basically change as a function of time. And so this is a parameter which you, to mimic various scenarios. For example, if you have a cyclic universe, or one which is ever expanding or it's contracting, all these things, you can do this simply by choosing a particular scale factor. And you can also then ask yourself, well, if I'm setting up an analog gravity system, what I can do is I can change the scale factor for the boson interactions. So how the interaction strength changes as a function of time. And when you work through the analogy, you can see, well, if you, for example, want to mimic a particular de Sitter universe inflation, you have to, depending if it's a two-dimensional or three-dimensional condensate, you have to choose a particular wave function for how you change the interaction strength. And the change in the interaction strength then is related to what's called this Hubble constant. And so you can basically mimic inflation in these systems. So for this small fluctuation in this condensate, these little sound waves, they see they're going through an inflation in the epoch if you do it right. So now, not so quick, okay. So how can we understand that if you change the speed of sound, or if a universe is expanding, why do you create fluctuations? Why is something happening? If I'm there, someone is tuning the speed of sound very quickly, why do we actually do something to this system? And the simplest examples of understanding that is actually parametric resonance. So it's a sinusoidal change, or a repetition can also be a succession of sudden changes in the systems, of interaction strengths, or simply the size of the universe. If you would go like this, the size will get larger and smaller, larger and smaller. So, and then you can, I like this very much because we encounter parametric resonance in many, many cases. For example, when you're sitting on the swing, you actually use parametric resonance to get up to crazy heights. Now, let me say, so the situation, if I want to, would be, if I want to think about this analogy to the universe, would be like a cyclic scale factor, and in our cases, we would change the speed of sound in a sinusoidal form in a manner. And this is basically already well known, it's parametric resonance. So this whole thing of the connection to the cyclic universe is just another way of looking at it, but parametric resonance is well known. So one particular nice thing, which I found on the web, and there's also a beautiful paper about that, and you find many videos. So this is a Tibetan singing bowl. And there's a nice explanation about it. So if you rub it with some rubber, it will show if you stimulate it in the right way. What is happening here, the boundary gets deformed in a particular way. In this paper it's nicely explained. And that drive is with half of the driving frequency. This is the characteristic, roughly half of the driving frequency is stimulated in ripples on the free surface. So now let's look at that. When it goes through a rapid phase of inflation and you create all the particles. So this is, I think, it almost looks like if you boil the water here, right? So it can even has such a strong effect that you actually form little droplet bouncing. Of course, the analogy is completely gone. It's a little bit of a vague analogy, but I think it demonstrates how you can actually excite fluctuations by using parametric resonance. And now let me show you, this is some simulations my student did, a PhD student, Andreas Finke. So what we do is we change the, first we take the Bose-Einstein condensate, we use this Wigner simulations, so we do the whole Bose-Einstein condensate, and twice of this frequency here we have the sinusoidal changes, and what you can see is what you can see is that half of the driving frequency you create here, what I'm plotting here is the amplitude, and here is the wavelength. So at a certain wavelength, I'm producing a lot of fluctuations in the system. So by changing the interaction strengths, you get all these little fluctuations in your condensate. And what we can see is here also that first they get excited, and also this is a superfluid, and you don't, you also have, if you like, later on we'll come back to the quantum aspects, you also have decoherence, you have damping of this mode. So first you stimulate the system, you create the fluctuations, then you stop, and they're damping out, just as in ordinary order, because of nonlinear effects. Now, okay, so this is parametric resonance. What about inflation, where you just have an ongoing expansion? There's also a very easy way to understand that. Again, sorry for using all these equations, but it's very simple. So you have a second order wave equation here. And what you can see is simply you have a frequency of a mode. Imagine you have a universe. So, and I look at a certain fluctuation. It's propagating in my system, it has a certain frequency. Now I have the Hubble parameter, it's a rate of change. How quickly is this universe changing? Now, if you can see, if the frequency of the mode is much, much faster, it doesn't care about the change in size of the universe. Because by the time the universe has changed, it has propagated many cycles, so it doesn't really care. You can almost, if this is much, much larger, you can neglect it. It's simply a plain wave. Now, if the frequency gets comparable to the Hubble frequency, already then I cannot describe it with a nice plain wave. Might be some Bessel function or whatever. However, when this thing becomes equal, when this then basically have this sign change, and you basically then have, it's not propagating at all anymore, it's just being dragged along with the space-time geometry, and this is when you excite this field more. And this is how it works. And people call it, wrongly so, somehow the super Hubble horizon modes. It's really just a statement of frequency of your mode and the time scale of the rate of change in the system. So if this mode here, the frequency, because of the particular setup, is time dependent, what you can see actually is that this, when this gets smaller at some point, goes beyond that, it's what people call across the Hubble horizon, is a super horizon modes, which just get dragged along with the space-time fabric. But what's really, so basically it's getting really amplified, which means that this ratio, this by that, is going below 1. And then, of course, at some later point, you can free this mode again, which is melting of modes, when this thing here becomes larger than h, or when h, for example, when the expansion changes. However, so this is the same mechanism. Parametric resonance perhaps is a little bit easier to understand. And the difference also here is that you not only excite a single mode, like half of the driving frequency as in the parametric resonance, you excite a spectrum of modes. So you have fluctuations, of course, you have a certain spectrum, which means the number of fluctuations with a different frequency or different wavelengths is different depending on the spectra, but basically you have all sorts of fluctuations and ripples in your condensate. Now, this has been done. And they call it the acoustic analog of the dynamical Casimir effect in a Bose-Einstein condensate. The person who has done that is Chris Westbrook, yeah, on the right. And they've done a beautiful experiment. Let me explain that. So they took a condensate, a Bose-Einstein condensate in a cigar-shaped form. And what they did is they changed here. They modulated, it seems, because you can also use the external trapping frequency to change the density of the condensate, for example, and change the speed of sound. You also, when you do these things, you quite likely also change perhaps the effective interaction strengths and so on. But important is, by doing this, by changing the trapping, the trap in a sinusoidal way, you basically excite in a similar way as in the Tibetan sound polar, so you excite these fluctuations. Here, of course, again, with half of the driving frequency, you expect you expect the most fluctuations. Now, let's look what's happening here, and that's very interesting. So this is time of flight measurements. You take the condensate, you switch off the trap, and what Chris has, he has a detector, which is like a mash. So he lets the condensate, when you switch off the trap, it really expands like crazy, falls down, and it, on this mash, then basically you can, from the position in the mesh, you can reconstruct its velocity. Because if I have a condensate, so the condensate, fluctuations have a certain velocity which they're propagating through. So the condensate has a 0 velocity. So everything which was in the ground state, the condensate of the system, that will stay in the center. The fluctuations that had a certain momentum, they will propagate out. So basically, I get the momentum distribution gets mapped onto space. It's like a Fourier transform, which really is. And so what he sees is, again, what you expect. So imagine this is not quite the case, but imagine it's roughly in the center of the trap, the condensate is roughly homogeneous, which means it doesn't depend explicitly on the position. When that is the case, what that means is that momentum is conserved. Now, if I excite a small fluctuation in a system, it has a little momentum. In order to have it conserve the momentum, I have to create a pair of it. One going to the right, and one going to the left. Or one going in this direction, and the other one in the opposite. Now, what that means, again, it's a per-particle process. So whenever I see one with a plus k, I expect one with a minus k. So here you see, what you're seeing here, these are these pair-created modes, which are sitting roughly at the half of the driving frequency, which I modify. So, and now comes to my favorite bit, and perhaps the outcome of this will also be a little bit frustrating, because this is about quantum, and I will make a very strong argument that perhaps, so we only have seen classical effects, and it's very hard in quantum fields in curved spacetime to really get quantum effects. So there's a question now. So when I look at these fluctuations, there comes this question: is this now classical? Are these fluctuations, do they follow a classical or a quantum statistics, for example? Are these fluctuations classical or quantum? So now I'm in a superfluid. Before, when we were in water, everybody would say, well, this has to be classical excitations. Now here we're in a superfluid. That does not necessarily mean that these fluctuations are quantum fluctuations. Depends on the occupation number. So if the occupation number is very large, these fluctuations just start to behave classical. So one of the things you can look at, I'm not an expert on this entanglement issues and so on, but there is an easy way to understand a little bit when in these systems how you can actually distinguish between when is a fluctuation classical and when it is quantum. And one of the ways is to look at its statistics, or another way is to look at correlations. And so whenever you create these fluctuations, as I said, you create a pair of fluctuations. One going to the right, one going to the left. They are correlated. So at best, at that point already, it means whenever I see the one, I see the other, they are perfectly correlated. They're classically correlated at that point. Now, one first way of going a little bit beyond and ask, are they quantum correlated, stronger than classical? So a nice way to look at going towards entanglement, you have to make, it's not very precise, it will make some more precise statements. One way of looking at it is the strength of the correlation. So what do I mean with that? So imagine I'm producing these fluctuations in my system, the right and the left loop. And then I can ask myself, of course, I'm producing one, I can say I'm producing this with a certain rate. But what are the fluctuations around this rate? And quantum correlations is when I say, well, if the autocorrelations, the fluctuations within this guy here, how much this fluctuates and this fluctuates, if the autocorrelations are bigger than the cross correlations, so the fluctuations with respect to each other, if the cross correlations are bigger than the autocorrelations, then you have the stronger than classical correlations. Now, in some cases, that can also then be mapped onto entanglement. But for this, you need to look at a different measure. It's not quite so clear if this simple statement, which also people refer to as a violation of Cauchy-Schwarz. You can also look at the covariance matrix and so on, and you can actually show that for within some restrictions, these things are the same. So you can actually ask when are these pair-created particles, which have the same mechanism, following the same procedure as in our universe, when are they quantum correlated, when are they entangled? So what Chris did, he has published that, but when he gives his presentation, he always talks about it. He did check, he has some mechanism to check if he can look at the statistics of the fluctuations. He can deduce it from the density-density correlations. He can basically calculate these guys here, and he can see if indeed are they classical or quantum. And he has published it, which basically means they're all classical. So how comes? Now we're here in a superfluid, 10 to the minus 6 Kelvin, and again he has done a perfectly classical experiment. So what is the reason for that? The reason is simply that when you have an analog gravity system, you start with some temperature, and the temperature is non-zero, and as I pointed out, remember you have quantum noise, but then you have thermal noise and so forth. So depending on the initial temperature and the temperature of the effect, it's difficult sometimes to associate one temperature to one effect because it doesn't have to have a thermal spectrum, but you could always associate a temperature to a mode, coupling a little harmonic oscillator to a mode and look at the temperature. And so there is a threshold of how hot is your system allowed to be initially. So 10 to the minus 6 was not enough. So that was the outcome. And perhaps maybe also the measurement wasn't, maybe he wants to redo it, maybe, it's not so, it could also be another, but it seems that he started with a PSA that was too hot. Coming back to this quantum, you can start with a superfluid. You may, for example, also as in our system, we had a perfectly nice correlated beams. Whenever we saw the positive non-partner, we saw the negative one. They were beautifully classically correlated. And of course, nobody would ever doubt that there is any quantum, ask for the question, are they entangled, because it seems nonsensical. I think in the other way, perhaps one should also not so naively assume just because you're working in this regime, that you will actually get quantum correlations. So the question of really getting quantum effects in these analogues is an open, has not been, I think nobody has ever shown this, has ever reproduced quantum effects. So, right. And however, these are beautiful systems precisely to study, how get aware of what's going on in the system, study questions of entanglement, of statistics of the field, asking all these questions. I think they are ideal for that. And I think I have no doubt that eventually someone, perhaps Chris or somebody else, will actually come up with an experiment to actually produce a pair of entangled phonons arising from such an analog gravity system. So there are people actually, I've also started to collaborate with Professor Peter Grüger in Nottingham. We're also trying to repeat Chris's experiment to some extent, and we're trying to go down to the level when we can see quantum effects. At the same time, I think Jörg Schmidmeier also has some very promising ideas and promising setups that he could also look for this kind of behavior. One of the things which I believe is very favorable for these experiments is to work with so-called atom chips. That's just fancy words for you can have a very controlled atom trap. So you can actually manipulate the condensate in very fancy ways, in very controlled ways, which are suitable for this kind of experiments. So, now we're coming to the last one. I said, so the first one was how black holes lose their mass. Then we moved on how are particles created in our universe. And the last one is how does, if you have a star and it's collapsing and it's not a symmetric collapse, it may acquire some angular momentum, or it has already some angular momentum. So when it collapses, it forms a rotating black hole. And there is a process, again, similar to the Hawking process, how a black hole can lose its angular momentum. And this process is referred to super radiant scattering, or also that some people refer to it as a Penrose process. So how is this working? So what is a rotating black hole? So a rotating black hole, in principle, does not only have a mass, it also has an angular momentum. It can also have a charge here, if it's this Kerr-Newman black hole. So a Kerr black hole is basically after a white Kerr, a rotating black hole geometry. And what you can show in these systems is that there are certain systems, a certain situation when, again, we have a scattering process. I will explain this. If I would send in something with norm 1, it would come out with something that's larger than 1. So it's again an amplification process. This time it's not as in the black hole. In the black hole is a very particular amplifier. It takes things from the UV and basically sends away this redshifted radiation. So it not only amplifies it, it also drastically changes the wavelength of what it is amplifying. Here you can send in long wavelengths into a black hole and it's coming back out again. So, and what it is actually, you have an inner horizon, which is the event horizon, and you also have an outer horizon, which is defining the ergosphere. And if something is coming in between these things, it can still escape, right? Not, of course, once it crosses the event horizon. But what you have to imagine is when you enter this region here, you have what's called frame dragging, which means nothing can counter-propagate. So at the moment a wave would come in, it would get dragged along with the rotation of a black hole, but instead of falling back in, it basically requires particle current or normal energy, call it as you like, and then it basically gets sent off again, and it has stolen some of the angular momentum of the black hole. So again, it's a process similar. This is amplification process again. Here, crucial is also again this inner horizon, which puts this boundary. But now you can see the spectra is very different because look at this thing here. I know I shouldn't use equations too much, but what you can see is this is the frequency of the wave I'm sending in, and this here is, like you can set to 1, is simply the azimuthal number. This is the angular velocity of the black hole at the horizon. So if the frequency becomes actually the minus should not be here, it should be plus. I'm sorry about it. If omega, so imagine this is a plus. If omega is smaller than this, the whole has a minus sign. If it's larger than that, as a plus sign. Only when this gets a minus sign here, then you can actually have again this amplification process, just similar to the Hawking radiation. So here it means that the long wavelengths of the systems, where omega is very small, that those are being amplified, while the small ones are not. So now coming back, is there a system where we can see such a fact? In fact, this drawing was actually it was by Science News, and someone was making this picture about the Vancouver experiments. He chosen the wrong geometry because that was a non-rotating black hole. This is a rotating black hole, as I will argue in a second. So it's very unfortunate, but it's very nice for me now to use here rotating analysis. So how can we get this system? And again, it's very simple. In fact, this is how we started to do some of our first experiments. We went to I didn't have a lab at the time, but I wanted to test something, so we went to the local tool store in Italy, and we bought this bucket where people use for decomposting their leaves and the garden. And what we did, we cut the bucket, we put a hole in the center, we took these holes in there, and what we did is basically we used some food dye to map out some of the fluid characteristics, and what we set up here is a stationary draining flow. It's very bad because we don't recycle the water at that point. But what you can see is this kind of geometry. So if I look at that, you can then think about what are the velocities doing, and you can basically look at the effective geometry arising in such a system. And what you can see is, so how do I get these two horizons? So the black hole horizon lies, again, when the speed of the surface waves is equal to the radial component of the flow. So now I have a two-component velocity field. One is a radial one, right, because the fluid is draining, and one is the angular velocity, because the way I feed in the water, I give it an angular momentum. So I have this two-component velocity field, and the black hole horizon is again when the radial component, when the radial velocity is equal to the speed of the surface wave. The ergosphere is given when the total velocity, radial plus angular velocity, is equal to the speed of sound. So here you have this frame dragging region, and here is this horizon. Now, if it would only have this horizon ascending a long wavelength, then it would just drown. Because for the Hawking partner, you need things that want to escape here, that get dragged in and sent back out. So the ergosphere is really crucial, but you also need this boundary condition for this scattering process to basically produce these negative normals. So, right, so again, I explained that already. You have these ingoing ones and the transmitted ones, and you can, again, in a similar process, you can steal some angular momentum from the flow to have this superradiant scattering of my surface waves in this faster vortex flow. So this is an experiment which we set up over the last couple of years. Some technical drawings here. At the moment, still in Italy. We're discussing of moving it to the UK now. This is the flume here. This is what we get from it, the vortex. These are the people involved here. And what we see here, we are now developing some very special, what we have to do, we have to map out the whole free surface of the flume. And that's a real challenge because we want to have very tiny amplitudes. So we use some very fancy mechanism which we're developing with a startup company in Germany, in Vienna. And rather than me explaining you the setup, they made this video, and my student Matt, who was also part of the Vancouver experiment, has such a nice explanation.
Essentially, the nice way to think about our experiment is that it acts like a very large bathtub. So the vortex that forms in the center here is very, very similar to the vortex that forms above the drain in your bathtub. Hence the name for this fluid dynamical phenomenon, bathtub vortex flows. Our experimental setup is 3 meters long, 1.5 meters wide, and 0.5 meter deep. What we do is we pump water out of our reservoir located beneath the tank. The water is pumped in through 2 inlet arms located on opposite ends of the tank. The rate of water that we pump into the tank is at about 6,000 liters an hour.
Sul lato della vasca è posizionato un generatore di onde.
Okay, so it's in Italian, but thankfully. Okay.
Could I ask,
Yeah.
Sì.
Good.
could
So.
I ask something? I'm
Yeah,
sorry.
yeah.
It looks orange, the water, is that just...
No. So in order to, I didn't explain this much. So we want to get the free surface. So the way it works, it's a bit complicated. I can explain this already. We put rhodamine dye in there. Rhodamine or fluorescent. We put fluorescent dye in there. And then what we can do, there are 2 ways. If you have from the side, if you have open channel flow, you have this block of water, right? And you put this rhodamine dye in there. And then you have like a power lens, a 2-dimensional light sheet. And then what you can actually get because of the luminescent effect, you can basically map the free surface. And the free surface, if you want to do this field theory experiments with things, has all the information, frequency, wavelengths, and amplitudes. And from this I can calculate the norming and everything. So once you have the free surface, you can reconstruct the spectrum. And what we do here with the 2-dimensional one, which is a real challenge actually, is what people usually do is called profilometry. We do something a bit more fancy where you would project a pattern, stripes, and then if the wave comes, it deforms that pattern, and from the deformations you can reconstruct the shape. Now with this company in Germany, they have developed something using 2 cameras. It's a better method. They have some random pattern they project, and And from this they can actually reconstruct the surface. And the challenge we have, because we need it over a very large area and a very high accuracy, so nobody has ever done that. So let's see if we'll get that going. So just currently, we think we're all set in some sense. We have just finished some theory discussions, studies, where we said, okay, one thing which, because you said, well, wait a second, aren't you just doing what everybody else has done for years and years, and you just give it a fancy name, call it analog gravity systems? Is it actually useful? And so I wanted to give an example why I believe it's very useful. So you can't read that very nicely, but what should be seen here is this is a parameter space. This A is related to the radial velocity, is a free parameter, and then B is related to the angular velocity. And then we can also change the height at infinity, right? So these are the three, if you want. So parameters, which it's a bit more complicated, the whole system, but within some approximation, this is what we can change. And what we then did, we did include some more fluid dynamics details. What we can actually calculate, we can say, okay, can we understand this amplification process? So I have a parameter space which is very large. This part here I cannot access because my approximation breaks down. I don't have a good description for it. This space here is hard to access because it's just hard to have such high flow rates in these kind of things. So here's my parameter space, and I want to find my points here. But what is the maximum amplification which I can get in this, and is it in the linear part of the regime? So it's a huge parameter space, and the challenge is now to find one point where we can do this experiment and where the effect is large enough to be seen. And for the large enough to be seen, it means what is the amplification? I send one in, what is times what am I getting it out? And what we can see is, this is kind of like what we did. We calculated actually fluid parameters. So these are things, for example, of constant angular velocity at the horizon. These are of constant surface gravity at the horizon. And then we calculate that and go from fluid parameters to analog spacetime geometry parameters. And then here we have the angular velocity at the horizon, here the surface gravity. And what you can see beautifully is that it mainly depends on higher angular velocity, but it also increases with increasing surface gravity. So, and one of the things also, Sabine asked me in the break and pointed out, so this analog, usually in a real rotating black hole, we can anyway only mimic part of it. But if you would only have this part, it would only depend on this quantity. Because I have another free parameter in here, it doesn't only depend on this, it also depends on the surface gravity. So I can see this effect. The spacetime geometry is a bit more complex. So, but you can still see this effect, and perhaps somewhere here we can do this experiment, somewhere 1.1, maybe we can see that. So this just, if you want to understand when this effect is the largest, it really seems necessary to have the analog spacetime geometry. So I think this beautifully shows that it's not just adding a new fancy way of looking at it, it really adds some value to the systems. Now I'm almost done. I have a few more things. So a long time ago, isn't that? 1980, I would say, the first analog experiment. It's not really an analog gravity experiment, but in this spirit was performed by Michael Berry. And he looked, I think I'm running out of time, I cannot really explain, I can do this later if you ask me, an Aronoff foam effect. It's an effect in quantum mechanics, and which is unobservable in quantum mechanics, says in his paper, and then says he finds a water equivalent of that. And what he does, he looks, so the Aronoff foam effect, let me quickly explain this, otherwise it doesn't make sense. So if you have a cylinder with a certain radius r, and there is a magnetic flux, the cylinder is penetrable, and you have a beam of particles with a charge. You see that these particles experience away from these locations, and you can quantify from the charge and from the magnetic flux, you can quantify a number, and if this is to the next integer of this number, you can calculate that. You can see that it gives you how many wavefront dislocations you have. So if this number is 1, you have 1, this number is 2, and so forth. And what he says, actually you can see that for surface waves if you have only rotation, no draining, only rotation. And he repeats these experiments here, and he says he can find the analog of this quantity, which he calls alpha here, and he can calculate the analog. And when I tune the things the right way, then I can reproduce this effect here. So these are surface waves, that's a theory. And what you can see if you take, for example, let's take the one which is very obvious. Let's take this one, and you can see already here that this corresponds to this situation. Now, why I'm interested in this, because it's an old experiment, I think it is really great, this idea. But now you also have to include the analog space-time geometry, and it was Sam Dolan and Oliveira, they did some studies, and they said, wait a second, if I not only have rotation, if I only have drainage, radial velocity, what I'm seeing then, I also have, on top of that, I have this effective space-time geometry, I have this frame dragging region. And what they said, okay, here, I'm sorry that the pictures are so bad, but what he's basically pointing out to here is the effect with zero radial velocity. If you take this into account, what you're getting actually, you get this additional pattern, which is caused by the frame dragging. So this is not just an analog for, it's an analog, basically. Here you can see some water equivalent of iron of foam, and you can also see some frame draining effects at the same time. So I think this is a very exciting system, and hopefully we will soon see some of that. If it's not us, also Daniele Faccio is working on this. He is using the fluid of light. It's a very exciting medium. It's graphene dissolved in methanol, and he basically, again, of course, he works on these optical systems, uses fluid of light, and he also wants to look for superradiant scattering. There is not more information out, so this is the only picture I found, but it's very good. So now coming to the summary and outlook, perhaps, and coming back to some of the question, what is it useful for? And right, so let's start with the very top. So what is the general idea to test some of these ideas in quantum gravity, in tabletop experiments, doing this analog simulation. The idea is, for example, the reason why we need to do this, why can we not study just the real world? Well, it's very hard to do, to have observational access to the system, like Hawking radiation. Cosmological part is what actually we do, of course, have some window of observation. But in all of these effects, they're very hard, they're very inaccessible. So by having these experiments, you really get some sort of feedback. You can set them up, you can study them, you can test their robustness, and so forth. And I think I should have also, there are some also, I don't know if there has been an experiment on radiation, but so far what people have done or working on are these kind of things. Here, you can ask another question. Could you perhaps at some point, because this is here about quantum gravity, could you perhaps at some point go a step beyond that and find analog systems for full quantum gravity proposals, perhaps more in the sense of quantum gravity phenomenology or other things. So, but can you actually try to mimic and test some robustness, perhaps the emergence of spacetimes, or already Horava-Lifshitz gravity in some sense has is a gravity theory, a full gravity theory with including Lorentz violations, which should add to the renormalizability to the theory. So there's a lot of feedback by basically joining these seemingly distinct areas in physics and trying to steal some concepts from one to the other and try to integrate all of that together. Because after all, physics has this amazing ability that it repeats itself. So, and now let's just say what are the things, particular these analog gravity experiments, what do they try to address besides of being cool experiments? So one of the things is how robust are these effects, which were predicted within quantum field theory in classical and quantum field theory and curved spacetimes. And in particular, I'm raising this question, well, you always just hear quantum field theory and curved spacetime, and also this is a workshop about quantum quantum gravity, quantum effects. I'd say it's very important to add this classical, because I think there is much more classical, at least in these analogues, as it is quantum, because the quantum things are very fragile. Entanglement and all these things, T coherence, initial temperature effects, all of that really makes it hard to access. But I believe soon there will be experiments. It's not I'm saying it's not impossible, but I'm saying you have to be very careful when you look at that. Right, how much, and it's also a question of how much can we control these systems, how much can we cool down a Bose-Einstein condensate, right? Can we actually cool it down to a point much below it has to be much below the chemical potential, which is very hard to do experimentally. And can we do that to a low enough temperature? Can we really see the analog Hawking effect? The analog quantum Hawking effect. So, and as I said already, can we also get some sort of feeling of how to do these experiments, how difficult they are? We have this highly controlled environment. Perhaps this insight, this knowledge we get, maybe it stimulates also to look for observational effects. And last but not least, as I mentioned anyway already, can we get some of these motivations or some of the insights from the analog gravity system, can we map them onto full quantum gravity proposal? Thank you very much.
Thanks.